Okay, so our final speaker for the symposium is John Pardon from the Simon Center. And he's going to teach us about universally counting curves on Calabi threefold.
So first, to begin, I think we should give the organizers a round of applause before. So before I talk about enumerating curves, let's get some motivation by recalling what happens when we try to enumerate points. So if we have in fact all the variables, they define our plane curves, and we can try to count the intersections of those. One equals 0, and classical statement, our Bezoos theorem, so this is the degree of f times the degree of g, provided we count in the triangle. So this is true. Provided one. So first of all, we have to count intersections at infinity. So f and g are both linear, those are lines. Generically, two lines intersect at a single point, but if the lines are parallel, then we need to remember that we should really be working in CP2, and there's some intersection here. At infinity. We're just forming to hold them to have a notion of number of solutions with reasonable properties. And second, we need to count with multiplicity. Parabola, and again generically there are two intersections. Transverse intersections always have multiplicity 1. In the special case where they're tangent, you just get one intersection point, but the multiplicity is good. So now let's move on to the counting curves. Take x. And let's look at the space. And the space is smooth. Smooth curves inside of it. Embedded. Now, if you want to count curves, you need to resolve these two issues, 1 and 2. We need the notion of counting with multiplicity on this space, and we need to make sure we have all the curves at infinity, whatever that means. So the easiest thing to resolve is number 2. So what does it mean to count with multiplicity? So one way of addressing this is the following. You can consider the space of smooth curves as an infinite dimensional intersection problem. So you can look at the space of all smooth maps from different domain Riemann surface based on X. And not all smooth maps will be holomorphic. This is a smooth space, but most of it's irrelevant for the space M. If given a smooth map, there's a way of measuring whether it's holomorphic. You take that anti-holomorphic True. And that's action of, I guess, I think it's the one we can consume. Whatever, it doesn't really matter what it is. And that's a zero set. And that zero set is the space now. Now, there's a slight lie here. I'm considering arbitrary smooth curves and with arbitrary complex structure on C. If you hear the way I wrote it, I really fixed a particular complex structure on the Riemann surface on the curve. So you need to say a few words about letting the complex structure on sigma there. The moduli space of Riemann surface is finite dimensional, so ignore that for now. So this is a finite dimensional space. Now this is expressed at an infinite dimensional intersection. You have an infinite dimensional base, an infinite dimensional vector bundle. Action. Here's the set of zeros. So it's actually quite a similar picture to the picture we started with. It's just happening in infinite dimension. Yeah. And so there's the analytic fact, which is that this operator del bar is elliptic. And what that means is that this infinite dimensional intersection problem is in some sense equivalent to of the flavor. So this gives a notion so there are lots of there are lots of technical theory involved in making this precise. I could say we're in perfect abstraction theory or 3D structure, but that's not really the point of the talk. So
Right?
bigger, yeah. Yeah. Oh, so this sort of says how to count curves with multiplicity. But the point one is actually much harder. So there are many ways of compactifying this. Counting at infinity basically means we need to compare. So I'll just review a sort of cartoon sketch of two ways which one can choose to compactify the space there, but there are many more. In fact, there's this paper by Andre almost 6.5 ways of counting. And they don't go through all of it. They're more ways. So first way I'll mention maybe. And you can consider call it prime. And it's this case of nodal curves. C together the map to X. Now everything is whole. The whole map. And for this to be a reasonable moduli space, we need to insist that there are only finitely many vectors in the C over X. So smooth curves can accidentally degenerate to singular curves. And those singularities could be arbitrarily bad. But some sort of fundamental miracle that if you regard your curve like the image of some map, then all you need to do is allow the very simple singularities on just for singularity and then now for technical reasons, making the generating functions work out nicely. We're gonna have this prime, which it says we want u to be non-constant on every active component. But that's not so important. You could drop that and just have a slightly different generating function related to the one I'll write down by changing variables.
What's the definition of morphisms of C/X? What do you mean?
So automorphisms of C, which are fused with that.
And
Important variable. So this space as I wrote it is non-compact because you can have a curve and just take its disjoint union n times for any value of that. That would still be a point as n goes to infinity, that's not. But if you fix the homology class of the curve, then it's so you want the generating function, add that as a variable. Oh wait, there's another way it could be non-compact, which is the Euler characteristic involved to mind. So if we fix the homology class and the Euler characteristic, then there's the Laurent series. Use variable u. Right, I just want to at least write down these definitions. You don't need to understand everything in the definitions. Understand the rest of the talk. In fact, that's the point. So there are also Thomas invariants. And roughly speaking, well, we got Gromov-Whitman invariance by regarding smooth curves as sort of images of maps, and we got Thomas invariance by regarding smooth curves as zero sets of functions. So the way you formalize, take the zero set of some collection of functions in analytic or algebraic geometry is to there's an ideal sheet. So now look at follows. In some sort of miracle, if this way of compactifying the space has a natural way of counting its multiplicity when X is dimensional. So I'm putting invariance. It's sort of it's straightforward to imagine. It's not so hard to imagine that there's a reasonable way of counting the multiplicity for these guys, because what I said over here doesn't really require the map from sigma to X to be in that understanding. This has a notion of counting the multiplicity even for X as symplectic math. You don't use the abstraction. But for the theory of Donaldson Thomas invariance, as far as we know, it's very important that X be analytic or algebraic. There's no known good notion of a closed subschema of almost complex. So this is one sort of there's a related space called the space of stable pairs. Now, I think I'm not going to try to explain what it means. I just want to write it down, illustrate the definition. But here she use with a section. And the definition is a little bit more complicated, but from the technical perspective, it's much more convenient because here your an object here is a close subunit dimension at most one. You have curves and points, and the points fly around the manifold, and that's they're hard to keep track of. Whereas in the space of stable pairs, somehow this was introduced by Andre Thomas in some ingenious construction to find a multiply space which gives the same invariance, but does not have these points of fly around the manifold. Every configuration here is before the line curve. So you can pick down the number. So calculating these is not so easy, but many calculations have been done. And there's a sort of surprising fact, which is that all the anything. It seems like these variants are equivalent. If you know the Gromov-Litton invariance, then you know the Donaldson-Thomas invariance. So you know all the other curve enumeration invariants, say for complex threefolds. So there's this meta conjecture that all curve enumeration invariants of complex threefolds are equivalent to each other by some possibly very complex change of variables. Now this contrasts a lot with the wide variety of ways you could compactify this space. There's no real geometric way of relating these two compactifications as far as I'm aware. I'll write down the conjectural relation between Donaldson-Thomas and Gromov-Litton invariant because it's very interesting. Takes a very interesting form. So this is a conjecture, small Microsoft open top under Conde, and I'm just writing down the simplest version there. There's complicated versions of essentially the same statement. But I'll just restrict X to the labial. Labial, in this case, just means that C1 of X is 0. So then, this generating function here is equal to this generating function under the substitution Q is equal to minus E to I. U is like the variable in the variant. Yeah, U is this variable here. And you'll notice that this is a formal Laurent series expansion around U equals 0. This is a formal Laurent series expansion around Q equals 0. And this change of variables sends U equals 0 to Q equals 1. Or minus 1, I guess. Not Q equals 0. Okay. And so it's not a priori e to the minus IU is not something you can plug into a formal Laurent series in Q. So for this to even make sense, we need the second part of the conjecture, which is this PT function. Rational. That formula series around Q equals 0, a rational function, and then you can expand around Q equals minus 1. So it's known in many cases known for so-called local curves. By work of Brian Conde and Open Cross Finder. The local curve is just the total space of the rank two vector bundle over a curve. So you imagine you go on putting invariance for the neighborhood curve on the local coordinate situation. And these computations are already very non-predictive. Now you might complain this total space is not compact, so any multiplied space of curves is probably not going to be compact either. So the way to make sense of curve counts on this target E is to consider with this C star action of scaling the fibers. For the equivariant counts to be defined, you just need the fixed set of the action to be compact, and those are the curves of the cycle supported in zero. That's one setting. No. It's also known for chord varieties or a block bundle, and for complete intersections in vector spaces. What they do is they take such a complete intersection and they degenerate it to something tart. And argue invariant field in the same way. I want to propose a new sort of way of thinking about enumeration of curves, and it's sort of formal, doesn't have much content. It's based on this idea of forming some group. Well, let's just recall. Familiar groups to get some motivation for that. So that's you can consider a theory of X, which maybe is better called a theory of vector bundles on X. We've given group vector bundles modulo the relation of E is supposed to equal E plus E double prime whenever you have so this satisfies some evident universal property. So if I have any map from vector bundles from a viewing group with just additive underscore exact sequences, then that map happens uniquely through the K theory. Some tautology of it. Classified Euler curve. So you can make similar sort of universal groups of any and many other contexts. So you can take K theory group polygons, two modulo translation, rotation, and set. And polygon to polygon. So a homomorphism out of this K theory group might be thought of as could reasonably be called like a notion of area. It's some way of assigning number to each polygon, which is invariant under rigid motions and additive when you cut. So this classifies area, And then there's a theorem, which is that, in fact, taking the area, this is a nice one. So there is no exotic notion of area for polygons in the plane. Now you can do the same thing. Polyhedra. In R3. And Hilbert's well, not the one of Hilbert's problems was about, you know, is this true? Is the same result true for polyhedra and R3? And they proved that that's not the case. He constructed this other. Variant. And in fact, this is a nice one. It's complete computation. A-period polyhedron. But in general, the groups are very hard. So, for instance, if you want this polyhedron hyperbolic space, I don't think this is meant. So I want to do a similar thing, but for curves and three points. Let's make some big Euclidean group, really generated in some sense by curve configurations. And we're going to quotient by deformation invariance. So that is, we're going to define the universal way of enumerating curves in complex threefolds, which is invariant under deformation. The first thing, the definition, Z of X will be the space of X. So one cycle is just curves with multiplicity. So they're not parameterized in any way. They don't have a substitute structure. They're just curves with multiplicities. And and this is a topological space. And a nearby point can be described by saying, well, each of these curves you can move a little bit. And it has a multiplicity, it's sort of split into a few different branches. So this curve multiplicity 2, you could split into, something that looks like twofold branch covered, which helps with it. And they can merge. You can also have minimal resolutions. That's informally what this is. And it's also a relative version. So if you have subversion, solve for complex manifolds. If it's submersion, fibers are complex manifolds, then this is the space of one cycles and fibers. The fact that we're doing the cycle in X. But I guess the points are the topology. Just the points. Just the points. Yeah. I guess it's a
There's no homomorphic anything, it just.
Oh yes, so right. It's all in the complex analytic category. So one cycle means like a complex analytic curve inside it. Okay. Yeah. Thanks for the complex chemical and one both operating.
Yes, so that's the space. Is there a group or that space?
Yeah, I guess there's a monoid structure at least, because I don't allow negative multiplicities. So one thing once our first attempt, I can make defining a protein for different things. Take all complex threefolds, and I'm going to take the three butyl group on compact and then three components of Z difference. Why is this a reasonable definition? So if I have a compact connected component of D of X, that's some space of curves, and I can say, well, the numerative invariant should be able to assign to that space of curves some number, element, whatever it is. And I'll quotient by something to impose definition there. So I look at all. Direct overall family, but of the same thing all time. Other development. Which is specialization at 0 minus 1. Okay. Maybe I'll call 0. Holds 0 compensation. This is your definition. But this you can call this. And I just read the definitions show that it's, the universal invariant of universal numerative invariant can be definition. From some tautology like these sort of definition. Now, here, this is sort of a useless definition unless you can compute the group you get. That's what we'd like to do. And if we can compute this group, then this gives a complete classification of all possible ways of enumerating curves. And you don't have to talk at all about how you can classify. You just know that whatever way you have of getting an invariant, maybe it's not by compact. Yes. It's the same thing as a homomorphism of this group. So before I go on, I need to say that, okay, this isn't actually the group we want to use. We want to do something slightly different. I've already given you a hint by replacing compact connecting components with H0 compact support. So in fact, what you want to do is you want to consider the entire check complex of the space of cycles. Not check homology of compact support. This allows you to add insertions to invariance. That's what it's called. And also, if you look at this this map here, you might realize that, well, there's no real reason to stop at one parameter factor. I could also like take a direct sum over all two parameter families over a simplex, and then have a map from that direct sum to here, which is a appropriate sign sum of the restrictions, but the three boundary fixes of delta two. For doing that, you can write down this bigger complex. And homology, I'll call. So this is the definition, which if I just wrote it down as the first thing, then probably would be. But it's, I'll try to explain why it's necessary to generalize the arbitrarily high dimensional. So theorem is that you take this group and you restrict to not just all. So I can't say anything about all cycles. I can't say something about the semi-final cycles. So I'll start over here. The semi-final cycles are the cycles where curves pair positively with the first term cross of X. So that's a crucial assumption. Yes.
Whose theorem is it?
My theorem from this is the three polynomial algebra on what we use the name for now, the local curve elements by the okay, so you think of these as indexing topological types of local curves, G's. The genus K is the Chern number of the zero section, which is gradient with zero since we're at the semicolon assumption. And the multiplicity of the zero section. So that's this one. And we restrict either the multiplication of one or the Chern number. So that's pretty simple. That's basically the best you could hope for some proof of this complicated definition, just to free on some generators. And okay, one immediate corollary is this defaults for the defaults. Now, I have to point out there's much more to be done for this conjecture. This hypothesis of everything being semifinal is really used in an essential way for this results picture. So I don't know anything. I'm not saying anything for I use a general type. Yeah.
So what's the degree of this element?
Yeah, I guess it depends on how you grade. I mean, it's if you grade it correctly, they're all sorry. Yeah. So I'm just saying, so in degrees, less than or equal to 0. It's in this free polynomial algebra, and all of these have degree 0. If you grade it correctly, you should somehow shift the grading depending on what you remember. So that the numerator and variance have degree 0. So I have to also say this is really inspired by work of Alan Parker on the Calabi conjecture. Integral. So you might have noticed when I stated this MNOP conjecture that one side, the Gromov-Witten side had Q coefficients, whereas the PT side had integer coefficients. And so if this conjecture is true, it's giving some non-trivial integrality constraints on the Gromov-Witten invariant. Some certain linear combinations are integers. And that is one equivalent formulation of this GV integrality conjecture. Certain linear combinations of Gromov-Witten invariant are in fact integers. So this was proven by Parker for symplectic threefolds. And if you look at their proof, you realize that they don't really prove this. They actually prove something much better, which is that they prove that all reasonable enumerative invariants of symplectic Calabi threefolds are determined by what they do on local curves. So they basically proved the analog of this assertion in the almost complex setting. In the almost complex setting, you can get away with simpler manifolds and invariants and one parameter family definition invariant. So once you realize that, it's then natural to say, well, what can I use this in the complex analytic setting? So if you remember, Donaldson, Thomas, Ponder, Thomas invariants, they don't exist in the symplectic world. They're only complex analytic objects. And so if you want to be able to say anything about them, you have to work in the complex analytic setting. Now this work of Alan Parker, it's based on generic transversality. It's based on this well-known fact that
Can I ask a question?
Yes.
So I didn't really understand how the corollary follows from there.
Yeah. Let's see. So yeah. So the point is, we're all putting variance define, homomorphism of a group. I think it's Q. So for this, basically you need the notion of counting with multiplicity to like exist in for families. And you need to know their invariant on their high parameter deformations of the higher homotopy to get this, but this is somehow standard variation on the construction. And then under Thomas invariants again. This. And right, the conjecture is that these two homomorphisms are, well, to prove the conjecture, it would suffice to say these are related by this change of variables. And so given the structure of this group, it suffices to check it on these local curve elements. And for these local curve elements are defined so that evaluating something else gives you the invariant for that local curve. And it's known for local curves by Openkopf, Brian Hunter.
Well, with the obvious condition counting this.
Yeah, so I guess first of all, it means that your invariance you can express the invariance you want as a cycle and semi-finite thing. So you need it for this. And of course, also can sort of comes in for degree reasons, so that you get something which you don't need any insertions.
I see. But the Gromov and appendage homers are actually homomorphic on the whole Gromov.
Yeah, yeah, so somehow. An element of this homology, this Gromov group, is like, you know, a collection of one cycles together with like an insertion. Right, it's insertions coming from, you know, homology classes of value on the space of cycles. So it's, but no descendant insertion, only this primary insertion. I don't, yeah, that's the other thing. I don't know how to say anything about descendant insertions from this. No. Let's say like 2 words about the group. So the work I did on Parker is based on well-known fact, the generic almost complex structures made of all simple curves. How about trying for you can think of this statement, this assertion, this theorem as some transversality assertion that, you know, you have a priori class and this is some configuration of curves you'd like to count. And you can always express it, decompose it into a bunch of isolated curves. We know in general. It's not really possible. It's possible under these positivity assumptions. This is why this is a crucial assumption. And this is what Eno and Parker used in their result, basically reduce any reasonable curve counting invariant for symplectic Calabi threefolds to what it takes values on, its values on isolated curves. So what can we say about generic complex? We salvage this statement. So it seems like completely unsalvageable. I mean, almost complex structures are objects of smooth topology. You can make compactly supported perturbations, these bump functions. These just don't exist for complex structures. If you have a projected threefold deformations of the complex structure classified by each one of the tangent bundles, so it's a prime dimensional group. Maybe it's even 0. Maybe you can't be formidable. So to salvage it though, what you can do is make your variety smaller. So if you take X and you put a curve in it, I'm not going to make C transverse by perturbing X, but I can make C transverse by perturbing the neighborhood of C. Yeah. Generic complex structures on neighborhood of any curve. Make all curves. Once you formulate the statement, it's not hard to prove. It's similar to the true for similar to the following statement. If I take a Riemann surface C and the point P, and I say, okay, I'm going to deform C as follows. I'm going to remove a neighbor. I'm going to regard C as a begluing of the complement of point and neighborhood of the point. So a disk around the point smooth over the puncture disk. So C is glued up of these 2 pieces, the disk and C minus P, intersecting over this punctured disk. I can change the gluing map. So given any vector field on the disk with some pole at P, maybe some higher order pole at P, I can use that to deform this gluing map. And by taking these, forming the gluing map in this way, I can explore the entire local moduli space of Fremont surfaces near this one. By re-gluing. So you can do a similar thing here. You pick a divisor, transfers the C, and re-glue the complex structure using some vector fields here. That gives you enough deformations to play with. So the weakening of this statement, the fact that this is sort of global deformation, this is like a local deformation nearing the curve, is responsible for the need to include all families of threefolds rather than just 0 parameter and 1 parameter families. Basically, in order to analyze some configuration here, you need to put yourself in a situation where you write your invariant as of a single threefold as an invariant of a family of threefolds with the property that for every point in the base, your configuration you're interested in consists of just a single curve for every point in the base, and then you're allowed. Then you can take advantage of this.
You mind side, you repair everything in the second window.
Yeah, so like, right, I need D to somehow intersect all the irreducible components of C. And then there are enough. Then regluing around D is not sufficiently rich to make C transverse. And it will make, yeah, so sort of a delicate statement because I fix a curve, but then of course, I do a deformation, maybe C isn't holomorphic after that, but it's all the nearby curves are transverse when you do this.
Other questions? John? So when you sort of change the complex structure, like the two curves are actually living in different places, right?
Yeah, yeah, the target is not different. But I think the new target has all its curves to be transverse, at least. And maybe I mean something slightly weaker. You could say, okay, you have a deformation. Maybe what I mean is that I think a better way of saying it is that there's a 1 parameter family of complex structures. Such that this curve in the central fiber is now transverse in a total space. That's a little bit weaker than what I said here, and that's what you actually need.
We have expectations for like a hierarchical module of this.
I think, yeah, not that I'm aware of, and somehow that the higher cohomology then is something about like high parameter families of curves of 1 cycles, and then when you have a multi-dimensional parameter family of cycles, it's going to develop like arbitrarily bad singularities. So then, yeah, that seems probably very complicated, unless there's some other miracle that happens.
Can you help me like relate these two pictures future? So the one on the left hand side, you said C isn't transverse, but you can perturb a neighborhood of it to make it so. And then how is that related to the next one?
Yeah, let's see. So,
There's no relationship, but I assume there is.
yeah, no, so I guess, yeah, so I made some assertion here, and it comes down, proving that assertion comes down to saying that, okay, some space of like meromorphic, so there's some space of meromorphic functions on like meromorphic sections of the tangent bundle of D. And given such a meromorphic section, you can sort of imagine perturbing this gluing map by flowing along that vector field. Get a new gluing map. So you get a map from this to the moduli space of Riemann surfaces. The tangent space of the moduli space of Riemann surfaces is C, which is an H1 of C comma TC. And my claim is that this was surjective. You could get all the local deformations of C by regluing the meromorphic vector. Now, my statement here was so that you can make C transverse after, again, doing the same sort of regluing. So the statement here is that regluing, I guess now I should say neighborhood D. And now, yes, the X. Meromorphic section, tangent bundle of X with poles along D, defined in the neighborhood of D. Those I can use to reglue, and when I reglue, this gives me a family, and in that family, I can ask, does C deform or not? So there's an obstruction going this C and whatever the deformation context of C is. So I guess it's the tangent bundle of X, maybe with modular tangent bundle of C. So that's the statement. So my statement here is that this is subjective. So yeah, it's slightly different cohomology groups in both settings, but the proof that they're surjective is basically the same. You can write down these maps concretely in terms of double cohomology. Use some Fourier series stuff.
So the anti-information theory of Calabi threefolds is very nice.
Yeah, no, so that's all about like compact Calabi threefold thing. So no, I to be able to do anything at all, we need to make it non-compact. Local.
There are expected symplectic analog of these PT.
I'm not people have thought about it, and there's some partial answers in like there are special cases for like very mildly singular configurations, but I'm not aware of anything close to like a general theory.
So what, are there any relation between this, like, homology theory with the Cho group?
Yeah. I don't think so. It seems slightly different, but it's definitely looks like almost the same idea. This is somehow, it's like, yes, yeah. Yeah, not that I really know. Yeah, so that's somehow why the semifinal condition is important. I mean, yeah, so when M is greater than 1, then those are multiple covers on the zero section, which is are allowed for Calabi dowels. Yeah, so I'd say the key step in proving this is just to show that the space of cycles can be, you can perturb things. So the space of cycles has dimension, bounded by its like virtual dimension, bounded by the term number. And transversality gives that to you under the semifinal condition.
So the semifinal corresponds to semi-positive.
So no one can ever remember the definition of semi-positive, but it's not this. It's something.
Just synthetic.
It's different. Semi-positive is different. It's not as easy to remember as this.
Other questions? All right, let's thank the speaker again. Right, I guess, that's it. Thank you all for coming.